Welcome to Oxidation Reduction Lecture B. Today we're going to focus on balancing regular oxidation reduction reactions, also known as redox reactions. I'll give you a moment to jot down these general guidelines for balancing redox equations. So we'll pause the video and then we'll do a couple of examples. So here comes our first example. The first thing we should probably do is make sure we can recognize who's oxidized and who's reduced, and assigning oxidation numbers would help that. So if we look at copper is 0 here in this case, it's a standalone guy. Hydrogen at +1, oxygen at -2, and hopefully we can see that the nitrogen here is a +5. On the other side, one of the things you'll notice is that we have NO3. NO3 is the nitrate ion in table E. So check that out. If you still have another nitrate, guess what? It's still +5 and -2. And our copper then, if I've got two sets of nitrates at -1, our copper must be +2. Oxygen here at -2 with two of them means -4, so nitrogen is +4, and good old water, hydrogen and oxygen are pretty trustworthy at +1 and -2. So let's take a look at whose charges or whose oxidation numbers changed. I can see copper went from 0 to +2. So I can see that's our oxidized guy. We also need to find something that is reduced, something whose charge goes down, and that would be our nitrogen here. Nitrogen goes from +5 down to +4. Notice I put those brackets in there. Those brackets help me a lot because they enable me to craft my half reactions pretty quickly. If I simply copy the tips of my brackets, copper 0, copper +2, I immediately have my half reaction crafted. I can balance according to mass and charge, like we learned how to do yesterday. Then I look at the other guy, nitrogen. Nitrogen there was at +5, and copying the tip of my bracket, it went to +4. And I balance it according to charge. And it's already balanced according to mass. So what we can see is that by being oxidized, copper has lost 2 electrons, and by being reduced, nitrogen has gained only 1. So I have to make the loss equal the gain. So of course, 2, 1, least common multiple is 2, so I can make them both 2 if I multiply this half reaction through by 2. So by doing that, multiplying the half reaction through by 2, I'm going to marry the half reactions as well. So I've got copper 0, and I drop down 2 electrons. Nitrogen +5 gets a 2. Then I hit the arrow again. Copper +2. And 2 nitrogen +4s. And of course, our loss equals our gain of electrons, and of course they land in the equation here, and I can cancel them out. What I have now is currently my net ionic equation. It's everybody that's undergone oxidation and reduction. So what I have in my net ionic equation, I have to put in my overall equation. I need 2 nitrogen +5s on the left. I currently only have 1, so I'm going to need to put a coefficient of 2 in front of the term containing the nitrogen. I have 1 copper on both sides, so that's good. And I need 2 nitrogen +4s on the right. So I'm going to put a coefficient of 2 in front of that nitrogen +4. And so now I can conclude my balancing by, I need to erase this so that I can make a table. I'm going to conclude by balancing the overall molecular equation by inspection. And that's something we learned about earlier in the school year. We know that we have reactants and we have products. We have copper, hydrogen, nitrogen, and oxygen. Back when we learned how to balance equations, making a little table like this could sometimes be helpworthy. We have 1 copper, 2 hydrogens, 2 nitrogens, and 6 oxygens. So hopefully we can see all that. And on the right-hand side, I'm going to need to do some erasing as well so that we can see what's going on. On the right-hand side, I have 1 copper, 2 hydrogens. Nitrogen I have all over the place. I call this a split source. So we need to account for all of our nitrogens. In copper 2 nitrate, you'll see I've got 2 nitrogens. And in the NO2, I have 2 nitrogens. So I have a total of 4 nitrogens. Oxygen is also all over the place. So I need to account for all of those. In copper 2 nitrate, I have 6 of them. And in NO2, I have 4 of them. And in water, I have 1 of them. So I have a total of 11 oxygens. Yikes. So I've got to fix some things. Do I want to start with the nitrogen or do I want to start with the oxygen? The nitrogen's in 2 different places, the oxygen's in 3 different places. So most likely we'd be more efficient if we were to look at the nitrogen first. So I have a coefficient of 2 present in front of the nitrogen. I need it to be 4 instead of a 2. So is it okay? Can I change this 2 to a 4? And the answer is yes, of course I can. Before I put the 2 there, it used to be a 1. I changed a 1 to a 2. Now I can change the 2 to a 4, and that's 100% okay. So what did that just do? Uh-oh, messed up my hydrogens, but that's okay. We'll fix them later. Did fix my nitrogens, though. My hydrogen counts at 4, my nitrogen counts at 4, and now my oxygen counts at 12. Oh boy. So now let's see who needs to be fixed. Now we have hydrogen and oxygen that need to be fixed. I've got 4 hydrogens, I've got 2 hydrogens. So I'm going to put a coefficient of 2 in front of the hydrogen containing compound and see where that gets me. It got me my 4 hydrogens that I needed. And now let's see what it did to our oxygen total. It took this 1 oxygen up to 2. And my other oxygens are still there. So I have 6 plus 4 plus 2 is 12 oxygens, which is exactly what I needed. So you'll see that my coefficient ratio is 1 to 4 to 1 to 2 to 2. I have the lowest whole number ratio of coefficients, and that's the definition of a balanced equation. Let's look at another example. Go ahead and see if you can assign oxidation numbers to all the elements in the compound. Okay, here we go. I've got +1 and, that's messy, +1 and -2, but I have 4 of them, so that's -8. So that must mean my Mn here is +7. You'll see that's a very high oxidation number, but it's definitely possible. Hydrogen and chlorine, +1, -1. Chlorine still -1 here because it's an anion, because it's a metal and a nonmetal. So with 2 -1s, then manganese must be +2. Chlorine here is a standalone of 0, and our trustworthy water. And what we will see is that manganese goes down from +7 to +2. That's reduction. So now I need to find somebody who's oxidized, and I did. chlorine here goes from -1, not here to this chlorine's also -1, but to this chlorine at 0. That is, charge goes up on a number line, so that is our other reaction. That is our oxidation half reaction. So let me copy the tips of my brackets, craft my half reactions, and there we go. Balanced according to mass, balanced according to charge. Next half reaction, I have to carry the little 2 with me because it's a diatomic molecule. Balance according to mass, balance according to charge. Aha, what do we see here? Our numbers this time are a little bit uglier. So I need to make sure my loss equals my gain. Least common multiple of 5 and 2, last time I checked, was 10. So this half reaction's getting multiplied through by 2. This one's getting multiplied through by 5. And I'm going to marry my 2 half reactions together. So I've got 10 and 2 Mn plus 7s and 10 Cl negative 1s, and I hit the arrow. And 2 Mn plus 2s, 5 Cl 2s, and my 10 electrons. And of course the whole goal of this was to make my loss equal my gain, so of course my 10 electrons should cancel. So now I have my overall net ionic redox reaction right there. Now I have to put those coefficients in place in my overall. So I need to have 2 Mn plus 7s, I only have 1, so I'm going to put a 2 there. I need to have 10 Cl minuses, I only have 1, so I'm going to put a 10 there. I need to have 2 Mn plus 2s, I only have 1 of them, so I'm going to put 2 there. And I need 5 Cl2s, and there we go. So I need to do a little bit of erasing again so that I can have enough space to show you how to balance the overall equation by inspection. So let's make a table. You can see these guys. We used to be able to sometimes balance just by eyeballing it. You can see these guys are a little bit more intense and may require a little bit more attention to detail. So a little table like this never hurts anybody. I've got 2 H's, 2 Mn's, got 8 oxygens, 10 hydrogens, and 10 chlorines. Other side, I have 2 Mn's, I have 2 H's, only in one spot. I only have oxygen in one spot, right there is my 1 oxygen. Did I have H twice? Oh, oops, silly me. Why did I do H twice? Oh my goodness, silly me. Let's try that again. Silly me, I wrote H twice. Try that again. H, Mn, O, and Cl. Yay, that's one less element we have to do. So, one more time. I have hydrogen in 2 spots. I have it in HMNO4 and in HCl. So there's 12 hydrogens altogether. There we go. 2 Mn's. I have 8 oxygens and my 10 chlorines. Now the other side. I have 2 Mn's. I only have H in one spot, looks like. There's 2 of those. I only have O in one spot. There's 1 of those. And I have chlorine kind of sort of all over the place. So let me do a little bit of erasing so that we can track our split sources of chlorine. Let's see what we have. I have 2 times 2 is 4 chlorines here, and 5 times 2 is 10 chlorines here. So I have a total of 14 chlorines. Okay, got that. What should I possibly maybe fix first? Do I fix the hydrogen and the oxygen in water? I don't think I want to quite do that just yet because I've got a bigger problem with the chlorine. I usually try to save oxygen for the very last. Hydrogen is usually next to last, and so do something else first, which is the chlorine. Check it out. I've got 14 chlorines on the right, 10 on the left. Look at where the 10 came from. It came from a coefficient of 10. Can I drop that 10 and change it to a 14? We sure can. Before it was a 10, it was a 1, and I changed it from 1 to 10. So now I can change it from 10 to 14. And there we go. That then gave us our 14 chlorines that we were searching for. But it also gave us now 16 hydrogens. And that's going to be a little bit more user-friendly to balance with 16 to 8 and that 2-to-1 ratio with a quick coefficient here of an 8. Gives me my 16 hydrogens, gives me my 8 oxygens, and we are now balanced with a 2 to 14 to 2 to 5 to 8 mole ratio. It is that odd number that made everything okay. That's all I have for you for oxidation reduction reactions, Lecture B. I hope